principles of chemical engineering in the context of methanol production are applied to the design and optimization of various unit operations, including synthesis of methanol, purification and separation of the final product. Firstly, a process flow diagram should be drawn, which is a graphical illustration of the major process units, piping and process flow paths. The key process unit for methanol production are splitters, heater, cooler, compressor, mixer, heat exchanger unit and reactors. Mass and energy balance are crucial tools used to ensure efficient and safe operation. Mass balance is an accounting for all mass inputs and outputs within a process. The equation is given as this. Whereas energy balance is an accounting of all energy inputs and outputs within a process. The equation is given as this. For methanol production, the overall chemical equation is given as this. Fluid mechanics in methanol production is essential in controlling flow and mixing of reactants, as well as the transfer of heat and mass within the reactor vessel. The fundamental elements of fluid mechanics are conservation of mass, energy and momentum, and the formulas are given as this. Fluid mechanics theories are applied in the design of reactors for the conversion of synthesis gas to methanol. These theories are used to determine the optimal reactor design parameters to ensure the efficient mixing of reactants and the removal of heat generated. Fluid mechanics also applied in the design and operation of distillation column used for purification of methanol, including the selection of appropriate column internals to increase separation efficiency and reduced energy consumption. In addition, fluid mechanics theories are also used in the design and operation of other equipments in methanol production plants. The friction loss of these components can be calculated from this equation. The Weymouth equation is used in natural gas pipeline design to calculate the pressure drop along the pipeline due to friction. This equation is used to calculate the pressure drop.
Our group have decided to choose reverse water gas shift RWGS membrane reactor and indirect carbon dioxide conversion method, as it is a low cost and secure way for producing methanol. First off, using carbon dioxide as a feedstock for the synthesis of methanol is possible thanks to the indirect carbon dioxide conversion process. Carbon dioxide is a greenhouse gas that significantly contributes to climate change. With the help of hydrogen, carbon dioxide is reduced in this process to create methanol. Due of its potential to lower carbon emission while also creating a valuable fuel, this technique has attracted attention. The second technology is the RWGS membrane reactor, which combines the RWGS reaction with the membrane separation method. As a result, high purity hydrogen and carbon dioxide stream, which are necessary for the methanol synthesis step, can be produced efficiently. The RWGS membrane reactor can lower production costs while also improving safety. The utilization of carbon dioxide, reduction of greenhouse gas emission, and reduction of high purity stream necessary for methanol synthesis are the reason we choose indirect carbon dioxide conversion method and RWGS membrane reactor to produce our methanol.
The process consists of a RWGS membrane reactor and a methanol synthesis reactor. A feedstock which contain carbon dioxide and hydrogen are divided into two streams. The main is sent to the RWGS membrane reactor, while the remainder part is required to adjust the composition of producing gas. There is an HSOD membrane for water removal was employed in the RWGS reactor, which can eliminate the intended separator after the reactor. As we have shown in the diagram, reactor walls were coated by the membrane. Water penetrates through the membrane layer during the reaction. A sweep gas nitrogen flows in the permeation site to carry the permeated H2O. CO2 and H2 are partially converted to CO and H2O by the RWGS reaction in an adiabatic reactor. The reaction products, which include syngas, CO, CO2, and H2, and water, are conveyed to a condenser to eliminate water from the stream, as it is a poison for the zinc oxide catalyst in the next reactor. The producing gas is then fed into the methanol synthesis reactor after transmission through a series of compressors and a heat exchanger to attain the desired temperature and pressure of the reactor. Boiling water in the sterile side of the reactor is used to control the temperature of exothermal reaction. Afterwards, the reactor outlet is transported to a separator to separate methanol and water as the condensable gases from the unreacted gas. Some part of the unreacted gas is recycled to the reactor to increase conversion.
Some assumptions that we have decided to use in this operation are 101.325 kPa for the pressure and 300 degrees Celsius for the temperature, while the feed flow rate that we use is 1000 kmol per hour instead of 0.64 mole per second due to its small value. Assuming a feed flow rate of 1000 kmol per hour rather than 0.64 mole per second may be practical, and larger units make processing huge number easier and decrease the chance of computation errors.
Diagram show mass balance for a reactive unit operation, which is the RWGS membrane reactor. We use table input, consume, generate and output to find the total output and calculate both input and output component mole and mass fraction. While for non-reactive unit operation, which is cooler, we simply calculate based on overall mass balance and each component mass balance as input and output are equal. Next diagram shows energy balance for reactive unit operation. We use method 2, heat of formation, and reference state of 300 degrees Celsius and 101.325 kPa or 1 atm as reference state to find specific enthalpy. Inlet-outlet enthalpy table and delta H formula were used to find heat Q. While for non-reactive unit operation, we simply calculate each component flow rate and specific enthalpy as well as inlet-outlet enthalpy table to find heat, which Q equal to delta H.
For the fluid mechanic part, we provide a layout of piping lines referring to our process flow diagram to show the flow of our fluid from the feed tank to our storage tank. The layout can be seen here. To calculate the pressure drop at our last equipment, component splitter to our storage tank, we need to use the principle of incompressible fluid calculation. Methanol that has been produced are an incompressible fluid. We assume some of the value that can be shown here. First, we use formula of Reynolds number to get the type of flow, which is 2805843.172 that are a turbulent flow. Then, we calculate friction factor, which is 2.505 multiplied by 10 to the power of negative 3, and our friction loss is 322.354. For the pump power, we use the formula here, and finally, we use energy equation to calculate the pressure drop at this pipeline.
As this pipeline has gas flow, thus we decided to use compressible fluid calculation for the gas flow. We use isothermal gas flow to calculate the pressure drop across all the pipelines. This is because most of the gas pipe flow is isothermal, as the temperature change is minimal or negligible since it's steady flow. First, we assume that carbon dioxide is negligible to simplify the calculation. Thus, we use hydrogen gas constant. For this calculation, we assume pipeline length based on the piping layout. For the first pipe, we calculate the pressure drop based on the following diagram. To start calculation, we calculate mass flow rate, friction factor, and assume first line is 50 meter. The calculation for this pipeline can be calculated like this. Pressure drop across the whole pipeline can be referred from this table. We use Excel to calculate pressure drop for the whole pipeline, as the application is the same as the previous calculation.
Next, for the strategy to deliver the main product methanol from component splitter to our storage tank, we decided to use a double wall underground storage tank system. A double wall underground storage system is one or more double wall underground storage tank that are connected using double wall piping and utilize double wall piping to connect the underground storage tank to our component splitter. In terms of double wall benefit, in the event of a leak, the interstitial area between the two walls of a double wall tank serves as secondary containment, thus preventing fluid migration and protecting the surrounding ecosystem. For the underground tank system, it enables the use of the accessible land for more commercial purpose. An underground tank system can hold up to 215 to 15,000 gallons fluid.
Strategy to deliver methanol from the final unit product to the tanks is by using the pumping system. The reason to use pump in the pipeline is to overcome friction and height difference between the pipeline. Next, for liquid, as we increase the temperature, the liquid viscosity will decrease. Then, the decrease in liquid viscosity will increase the flow velocity. Thus, the increase in temperature will increase the methanol flow rate.
In conclusion, the development of a methanol production plant is a challenging project that needs thorough planning and execution. It is important to consider the energy efficiency, capital cost and environmental impact of different plant design for optimal production of methanol. In end, we managed to design a methanol production plant that is low cost and safe to be operated.